Hello guys, welcome to my channel Civil Engineering Nepal. Uh, today in this tutorial video we are going to learn about flexibility method. This method is for the analysis of statically indeterminate structure. This method is also called force method, sometimes consistent deformation method, and if you are using it in matrix form, it is also called flexibility matrix method also. Okay. In the given question, we have four unknown reaction, that is horizontal reaction at A, vertical reaction at A, horizontal reaction at B, and vertical reaction at B, if this is support A and this is support B respectively. Support B. Here are four unknown reactions, but we have only three static equilibrium equations. So the degree of indeterminacy for this structure is equal to 1. Now we need to remove one unknown reaction, that is either HA or HB or VA or BV. Any one of this reaction among these four we need to remove to make this structure statically determinate. For this we can degrade any of this support, that is here is hinge support on both sides. We can degrade any of the support. The basic thing we need to know is that we can degrade the support but we cannot upgrade it. Now for this system, now for the computation of this numerical, now we will remove HA, that is we will degrade this hinge support to a roller type. Okay, HA is removed as a redundant, and we have degraded the support A to a roller type. Okay, now after degrading the support, the horizontal reaction at A vanishes. Similarly, since there is no any horizontal reaction acting on this system, the horizontal reaction at B also reduces to 0. Now we have removed the horizontal reaction at A, that is now we need to apply a unit kilonewton load at support A. Okay, now for the calculation of reaction, I will show you in the slide here. For the calculation of reaction for both the system that is M and M1, where system M is a real system and system M1 is a dummy system. Real system is the system with all the loads, whereas the dummy system is the system without loads, but only a redundant load. Okay. To compute the reaction forces at real system M1, we take the moment about point A equals to 0, and after getting a reaction, the one unknown reaction can be calculated by taking the vertical upward forces sum is equal to 0, that is taking moment about point A, we get the value of BV, and after getting the value of BV and from this reaction we can calculate the reaction at A, vertical reaction at A, by taking the sum of vertical forces is equal to 0. In the same manner, we have added a redundant load at A, and due to this load we get a horizontal reaction at support B also equals to 1, and due to this horizontal reaction we get the reaction on this support B and A, vertical reaction equals to 2/3 kilonewton. Okay, taking moment about point A in dummy system, we get VV equals to 2/3 kilonewton, and Fy is equal to, and taking sum of upward forces or vertical forces is equal to 0, we get vertical force at A equals to 2/3 kilonewton, and taking the sum of horizontal force is equal to 0, we get the horizontal reaction at support B is equals to 1 kilonewton. Okay. Now this is the reactions, reactions for the system after computation. That is it is the same figure as I have shown you earlier. You can also tell it as a free body diagram. Okay. Okay, now to apply the compatibility equation, we will discuss that one later on. Compatibility equation, we will discuss it later. Here we have to calculate moment for all the members, that is, see, here are members I'm sorry. Here are members AE, EC, CD, and DB. Now for AE, EC, DC, and BD, we have to calculate the moment for both the system, real system and dummy system, taking their respective limit and origin as per our easiness. Limit is fixed, whereas the origin can be taken as per our easiness or as per our desire. We can take the origin. Okay. In this way I've shown you the figure, I've shown you the table for the moment for the system M and system M1 for all the members. For AE, for the member AE in real system, the moment is X, whereas in the dummy system the moment is equal to 0. For in the same way, for member EC in the real system, the moment is equal to -6 plus 2 over 3 X, whereas for the dummy system it is equal to 200X. In the same way, for member DC, moment in real system is -6 plus 2 by 3 X, whereas in dummy system 200 minus 150 X minus 3. In the same way, BD, for member BD, in real system the moment is 2 by 3 X, whereas for the dummy system it's 250 X. I'm sorry, this moment is for dummy system, whereas this is the moment for real system. Okay, you need to memorize this M as M1 and this as M, capital M. Okay, I've done a simple mistake here. This is not M1, this is M, whereas this is not capital M, this is M1. Okay, just you can memorize it. Memorize means you just know that this part is mistake. This is M1 and this is M. This is a very simple mistake. Okay, now as I've said you just earlier about compatibility equation, right? This is the compatibility equation for a single redundant system. For a single redundant system, the compatibility equation reduces to delta 1 L plus R del 1 1 equals to 0. For a multiple redundant system, the compatibility equation changes as per its requirement, for which we will discuss in our next video. But for a single redundant load, the compatibility equation is delta 1 L plus R del 1 1 equals to 0, where delta 1 L is equals to integration of M1 into M dx divided by EI summation, whereas del 1 1 is equal to summation of integration M1 into M1 dx by EI. That is, now for delta 1 L, M1 into M dx by EI, and there is summation. That means you need to multiply this and perform integration, plus this and this into this and integration, and this into integration, plus this into this and integration. Okay, and for del 1 1, that is M1 into M1 dx by EI, means this is M1, this into this integration, plus this into this and integration, this into this and integration, and this into this and integration. Okay, now now calculating delta 1. Okay, I will tell you one small technique to memorize this relation delta 1L and del 1 1. How you memorize is that you need to remember that letter means real system, whereas number means dummy system. Okay, now in delta 1L, here is a number, that is, now we have a dummy system M. Now but the number is 1, so the dummy system is M1. Now letter means real system, that is, there is only one real system, M. Now in del 1 1, here is a number, that is, we have a dummy system. Now for a number 1, we have dummy system M1. Similarly, here is also a number, that is dummy system M. For a number 1, dummy system M1. In this way you can memorize this formula or relation. Now as we have discussed earlier, the value of delta 1L and del 1 1 can be calculated. Delta 1L is calculated as -11700 over EI, and del 1 1 is calculated as 180 over EI. you can perform a simple integration and summation, and you can obtain this value. Now we will substitute these values in compatibility equation. Now we need to replace we need to substitute delta 1 L by minus 11700 over EI plus R is the value of reaction we have to calculate, that is, it is the reaction we have removed in horizontal support, in support A, that is, it is the horizontal reaction at support A. Now del 11 we will now we will substitute del 11 by 180 over EI, and we will get and upon the substitution of these values in this equation, we get the value of R, which is equal to minus 65 kilonewton. Okay, here the negative sign indicates that the direction of reaction we assumed in the structure is opposite. So we need to correct the direction, that is, since we have assumed the direction in negative x direction, now the direction for horizontal reaction is in positive x-axis direction. Okay guys, this was the video. Don't forget to subscribe our channel, and also do like and share the video. You can also comment down for any improvement if required, and you can also share this share this video with your friends, classmates, etc. Stay tuned for the next video. Okay, Jai Nepal. Thank you so much for watching this video.